right. Let's do some statistics. All right. So, let's start wherever you want to start. Okay. Number one's a great place to start.
You said this was going to be a take-home exam, right?
What's that?
You said this was going to be a take-home exam.
I don't remember saying that.
I'm pretty sure I did.
No, I don't think so. I'm not that much of a pushover. Come on, jeez.
Well, you guys pretty good.
Hey, we had two
Now I can.
class tests. We have two.
Not a pushover, but can you be bought?
Could I be bought? I can't be bought. I shouldn't say that. I could be bought.
You could. Bring you coffee.
If it could fund,
You're not a pushover, but you're that awesome, though.
if it could fund my retirement, I could be bought. If I didn't have to work. Sorry.
I mean, if you make it a take-home test,
All right.
you don't have to work, you wouldn't have to show up tomorrow.
I know. It's tempting. Yeah.
What if we all push that?
All right. No, we're taking a test, and everyone's gonna do great. So don't worry about it. Okay. So number one is talking about calculating critical values. So let me pull up my e-text while we're working on this. So the idea here is you can calculate an interval for any amount of confidence. It's not too tough. Sometimes you just have to go get the z-values from scratch because they're not one of the common ones. So here we have a 97% confidence interval. So we're talking about 97% confidence. So if you have 97% confidence, what's your alpha level? Yeah. That's a 3% alpha level, which means, yeah, your alpha over 2 would be 0.015. So what we're really looking for here is z sub 0.015. So we're looking for the z value where 0.015 is above. So if 0.015 is above, how much is below? 985, because it's 0.15. So it's 1.5%, which means 98.5% would have to be below. So we're going to our table basically and looking for the 98.5 percentile. You could look it up on the negative or the positive side. So let me pop up to my z table. And we'll just go to the positive side because I had already gotten that. So we're looking at 0.985, and it looks like you hit that somewhere. Oh, it's exact. It's right here. So 0.985 is at a z-score of 2.17. So this would be 2.17, which I'm hoping is the answer that the back of the test had, or the C or D or whatever number it was. B. Okay. All right. I sure am. 0.015. Yeah. Right.
We can be able to have a page of notes and our Z tables?
Yes. I'll provide a Z table and a T table.
What is the difference between the margin of error and the alpha level?
So your alpha level is based on your confidence. So I mean, up front, right? You set a confidence level set at the very beginning. So you set your confidence level to say 95%, and whatever your confidence level is, that drives your alpha level. So like a 95% confidence interval, it corresponds with 5% alpha level. Remember your alpha level, so you can think of sort of like your error rate. It's the type 1 error rate. So the alpha level is fixed up front based on your confidence. The margin of error, so using that alpha level, you go get that z multiplier like we just did. The margin of error is that whole stuff that you add and subtract. That whole thing put together. So after you take your alpha level and go get a z multiplier or potentially a t for a t interval, then you go multiply all this stuff together, and that value that you're going to add and subtract, that's your margin of error. Yeah. All right, so your margin of error can change based on your results and your sample size and all that stuff. Your alpha level is fixed at the beginning based on your confidence level. Yes. Want you to notes? Yes.
So your confidence level and your alpha level all to 100.
Yes, exactly.
And then the other just 100 being the awareness.
Yeah, the margin of error changes, yeah, based on your sample. Absolutely, yeah. So your confidence level and your alpha level always add up to 100%, basically. That's right. They're complements of each other. Always, always, always. All right. Great questions. What's next? Number 3. So number 2 you should be able to get because you have a formula sheet. But I think the answer is B. So number 3, an article. It shows 46% would like more discussion about families' finances, 37% want more about school, 30% want more about religion. These and other percentages were based on a national sampling of 522 teenagers. Estimate the proportion of teenagers who want to talk about school. Use 99% confidence level. Okay, so some of these percentages are completely irrelevant. All that really matters is these people right here. 37% want to talk about school, right? So we're going to go do a confidence interval with, it looks like our p hat was 37%, and our sample size was 522 teenagers. And our confidence level, they want 99%, right? So then that Z multiplier is going to be 2.575. So that you can get off your Z table because 99% is one of those common levels. Okay, so we're going to use 2.575. And then now we're just going to plug it all into the formula. So the formula says we need to go 0.37 plus or minus 2.575 times the square root of 0.37 times 1 minus 0.37 all over 522. Yeah? Everybody okay up to that point? Yeah? Follow? Yes.
So what's the 2.575? What's that called?
This is so for the formula we have to have this Z alpha over 2 part of it. So that's it's based on your confidence level, right?
So whenever I say confidence level is 95 or something, we look into here to see the 95.
Yeah, if you're doing like 90%, 95%, 99% confidence levels, the Z values are already tabled on the back of your Z table. The only time it gets weird is if you have to go do some percentages like a 97 or 98% confidence level. But I don't think on the exam I would ask you any of those weird ones. I'll probably only give you like the standard 90, 95, or 99%. Yeah. Yeah. So,
On the exam, is it going to be multiple choice? Or?
probably. So I'm going to go ahead and you guys try to get that margin of error with me. I'm going to get that myself, see if my little iPhone can handle this. And then I get 0.0544. So this number right here, this is your margin of error. And again, remember, and actually I had an online student ask the same question that you asked yesterday, Stephen. Order of operations says we got to do all this junk first, and the add and subtract is the last thing we do. Yeah. So then we go 37% minus that. That's going to take us down to what, maybe 0.3156 or something ish. And then go up, that's going to take us to 4244. Thinking? And that's going to be our interval. So I'm guessing this might round it a little bit. Oh, it just wants this. Yeah, so it's 0.3. It looks like it's this one right here, B. So it didn't actually need the lower upper bound for that particular one. All right.
So
Yep.
when they want a lower and upper value, that's when we add and subtract, right?
Mm-hmm. That's right. All right. Anything? All right. Anything from 4, 5, or 6? Anybody have a question or want to see one of those done? So 3 we just did. That was calculating confidence interval about a proportion. Anything from 4, 5, or 6? Okay. So number 4 is where we need to estimate the sample size. So how large do we need to be 98% confident that the sample proportion will not differ from the true proportion by more than 3%? So this is where we're setting a goal on our margin of error. and we need to estimate a sample size. So if you go look up the formula, I think we have a formula for that. It's something like n equals, isn't it 0.25 z alpha over 2 divided by the error squared?
Yeah.
Is that true?
Yeah.
Okay. So this is for proportions, and remember, you have to know whether you're dealing with proportions or means. That's kind of the trick to this whole thing. So here, what's the error rate that we're trying to achieve? 4. We're trying to get our error down to 3%. So then our our goal is 0.03. What's our alpha level here?
0.02.
Yeah. Right? Because it was 98% confidence. So our alpha level was 2, which means alpha over 2 is 0.01, which means we need to go get that z value off our table.
Give it to you on the little chart.
Oh, is 98% on the chart?
Yeah, so it's
Oh.
2.33.
Nice. So there you go. So 2.33. So for 98% confidence, we're going to use a multiplier of 2.33. So we got everything we need. That 0.25 is just to be conservative. And then you say, okay, so our alpha is our z value is 2.33. Divide that 0.03. That's the error we want. Square that. And what do you get for that?
1,508.027, and then you just round it up to
What was your answer?
1,508.027.
So 15.8 and some change,
Yeah.
which we would round up to 1509, just to be safe. Yeah, 1509. B? All right. All right. Yeah, so all our formulas are in decimal form. All our percentages need to be converted to decimal form.
Yeah, but like, is it, if there's percentages, it would be a proportion?
Yeah. Yeah, a percentage is synonymous with proportion. But percentage, we have 2 decimal places over, and proportion is 2 decimal places. So mathematically, we think of them as proportions, but in reality, we're just so comfortable with percentages. We report them that way. All right.
What formula is used to calculate the
Confidence level is fixed,
Yeah, you just said that.
right? Yeah. Yeah, your confidence level and your alpha level are fixed ahead of time. Boom, this is what they are. You choose that up front, or I would give it to you. Yeah, there is no calculation involved in that. And it's all based on that type 1 error rate, type 2 error rate kind of stuff we had that discussion about last Thursday. All right, yes?
Your brother already said this, but are we allowed to have a page notes?
Yes, you are. All right. Let's see. True or false? If no estimate of p exists, we can use 0.5 in the formula. Is that what we did? That's true. Yeah, we did that. What's not a characteristic of the student's t-distribution? Is it symmetric? Is the t-distribution symmetric?
Yeah.
Yes. Does it depend on its degrees of freedom?
Yes.
Yes. For large samples, do the t and the z distribution look the same?
Yeah.
They sure do, but it does not have a mean of 1. It has a mean of 0, just like the z distribution. Okay. All right. What else? Where do we go now?
7.
Okay. So now we say, all right, now we're moving on to the point where we're talking about sample means rather than proportions. The problem is that we can't do z intervals, so we have to substitute with t intervals, which means now we need to use our t table rather than our z table. So we're looking for a t-value with 0.005 to the right with 28 degrees of freedom, right? So on the t-table, ooh, that was cool. So on the t-table, 0.005 is what we're looking for, right? With the degrees of freedom 28. So we just need to go to our T table, which is a couple pages beyond our Z table in the book, but some of you guys should have one. Here's our T one. So T sub 0.005, that means we're right there on this column right there. Scroll down to 28 degrees of freedom. There it is right there. And it looks like it's what? I'm getting 2.763 is what I'm seeing. Well, now I'm not seeing anything. Yeah, 0.005. Mm-hmm. So I'm seeing 2.763. All right. That's what I think it is. Yeah, right there. B. 2.763. All right. Cool. Number 8. You want to look at that one?
Yeah.
Takers for 8. Okay. I don't know if we'll make it all of them, but we can try. They're looking for information about savings accounts. They take 15 samples. Nice thing about T intervals is that small samples are okay. So that's the other cool thing about them. The mean balance was 686.75, so that tells me we're talking about averages or means, sample means. Standard deviation of 256.20. 98% confidence interval. All right. So the formula, since we're talking about means here, is x bar plus or minus T alpha over 2 S over root n. Okay, because we're talking about a mean. We already know the sample mean and the sample standard deviation, the sample size. They gave that information to us in the problem. What we do not know is we do not know this T alpha over 2. So what is our alpha level here? So it's 98%. They asked for a 98% confidence interval. So that would be an alpha level of what? 0.02, which means alpha over 2 would be 0.01. Yeah?
Because you divide the top.
Yeah, 2.02 divided by 1. Yeah. Which means, so then what our degrees of freedom here, if there was 15 samples, what's our degrees of freedom? So we have 14 degrees of freedom. So we're looking for T sub 0.01 with 14 degrees of freedom. So T sub 0.01, I'm on this column with 14 degrees of freedom. It looks like it's 2.624. 2.624. So that's going to be my multiplier for my confidence interval. All right. So now I got everything I need because our sample mean was 686.75. Right? Our T multiplier is 2.624. Our sample standard deviation, 256.20. And we sampled 15 people. So we're just dropping everything in where it belongs. All right. The hardest part about a T interval is finding the T value. Once you got that, then it's just plug and chug.
The degrees of freedom is just 1 minus the total number, right?
One less then, yeah.
Yeah, that's fine.
Yep, it's always one less.
Where did you get the 2?
So from the problem. So from the problem, they gave us the sample mean, 686.75, and they gave us the standard deviation, 256.20. All right. So what do you get for that margin of error or all that junk over there?
173.579.
173 point something.
579.
Okay, I got some questions real quick. What's up?
Where did you get the degree of freedom again?
It's always, so the degrees of freedom is always n minus 1,
Oh, okay, so there was 15 freedom.
15 samples, so 14 degrees of freedom.
What is over the end? Like in the, instead of 5 or 2? In the, like the formula. Yes, that one.
S.
Okay.
That's a sample standard deviation. Yeah. What was it, 173 and some change?
173.579.
Other people get that? Like 5.8? Yeah. So that'd be your margin of error. And then you would, add and subtract that to get your bounds. So go down 173.58, and what do you get?
513.17.
513.17. Add that.
863.
863. What?
860.33.
Yeah. So it looks like C. Yeah. By the way, could we have actually known the answer to this problem before we even did all that work?
Yeah.
Why?
Well, you can probably subtract standard deviation from mean.
I think there's an easier explanation, actually. What's the confidence interval always centered around? What's in the very center of the confidence interval? The mean, right? So that means my confidence interval better go above the mean and below the mean, right?
There's only one that goes above the mean.
Yeah, think about this. This confidence interval, and this confidence interval, they're all entirely below 686.75. So there's actually no way you could possibly end up with that with any of those three as your confidence interval, turns out.
Don't you want us to short order?
Sure.
But don't you also say that it doesn't really matter if we don't short order?
You could save Becca.
Sure. I assume if you get the correct answer, you did not cheat. That's what I say.
Can you go back to the other
Not all of them would be like that, obviously. Some of them aren't so easy to guess on.
So it doesn't always work.
What's that, though?
What?
Does it always work? Who said that?
You said so it doesn't always work.
Yeah, I mean, because I could easily include a bunch of intervals that are centered around the mean. Right? That one just happened to include a bunch of intervals that weren't centered around the mean.
Now you're going to go through the test and make sure they're all centered around.
So you can rule that out. Okay? All right. But if you did the order of operations incorrectly, there's a good chance you would come up with one or two of these other answers. All right. What else? 18. We'll get there. Let's go in order this time and see if we can. Any questions on like 9, 10, 11, or 12? Any questions on that one? No? Anybody want to see those? Okay. So 9 is another sample size estimate, right? So for number 9, it's saying try to figure out a sample size that'll get our margin of error down to 2 ounces. But now we're talking about estimating averages. What the heck's going on? So we're talking about means here. So when we're talking about means, our sample was, what is it? Z alpha over 2 times S over E squared. Is that correct? I think I remember that correctly. Yeah. So in this case, you go back here and you say, okay, so 99% confidence, what's our Z multiplier then? It's always 2.575. The estimated standard deviation, S, from previous studies was 7. The problem told us that. And the margin of error we're trying to get down to is 2. So this is what we're going to do to calculate that. So 2.575, multiply it by 7, divide that by 2, and square it. And what do you get? I want to say 60, 70 in there somewhere. Oh, 80 something? 81 point something, something, something. So we always round up to 82 samples. All right. So the key is for sample size, and this is sort of the whole crux of everything here, is that you have to know here we were talking about a proportion. That's why we use this formula. On this problem, we're talking about a mean, so we got to use this formula for sample size. So it's all based on what you're estimating. All right. Cool. 80. So what is it? 82.
Would it be 82 or would it, yeah, 81, because it was 81.22.
So for sample size, we're always trying to be conservative. So we would rather oversample than undersample. So we don't actually round following rounding rules. We just always go directly to rounding up. Yeah. All right. What happens when you increase sample size?
The mean gets.
The width decreases. Yeah. All right. Two-tailed hypothesis test means the alternative would be what? Two-tailed is a not equal to alternative. All right. Why do we never say except H not? I talked about this yesterday.
You guys just want to confuse people.
Because we're statisticians and we like job protection, so we make it confusing.
Yeah.
That's part of it, yeah. Most people won't admit that, but we do it. No, I'm just kidding. So, what is the real reason? Yeah, I told you about it yesterday.
Because you're not saying you're agreeing to it, you're just saying it's not what the alternative is.
That's true, but technically there's a good reason for it.
You said because there's no evidence.
No, I mentioned it yesterday. Remember, our alpha level fixes our type 1 error rate, but technically we don't actually know. Our type 2 error rate changes based on our sample size. And so since we don't know the type 2 error rate, then that's why we actually don't conclude an acceptance of the null hypothesis. We just say that we couldn't reject it, and that this is the reason right there. It's because that type 2 error rate isn't actually known. But if you reject a null hypothesis when it was actually true, what did you do? You committed a type 1 error. That's right. Are type 1 errors and type 2 errors independent? Are they independent events? Why? Yes or no, and why?
They're not because they're one kind of depends on the other.
Yeah. So they're not independent because one affects the probability of the other, right? As you drive up the probability of a type 1 error, what are you doing to the probability of type 2? You're driving it down. So they interact with each other, so they're not independent. Yeah. In fact, actually, they're completely dependent, because if I tell you you made a type 1 error, is it even possible that you could have committed a type 2 error? It's not even possible, right? If you do a hypothesis test and I'd be like, oh, sorry, you committed a type 1 error, that means you definitely did not commit a type 2 error. It's impossible to do both at the same time. All right. Let's see. 15? Hey, maybe we'll make it through all of them. Hey, this test wasn't that bad. You guys are going to do great. All right. The mean monthly gasoline bill for a household is greater than $120. If a hypothesis test is performed, how should you interpret a decision that rejects the null hypothesis? I feel like I'm missing a sentence there or something. What are the directions over there? Oh yeah, so a hypothesis test is performed. How would you interpret a decision that rejects the null? So if you're trying to show that the mean monthly bill is greater than 120, what would be your null hypothesis? So yeah, the null would be, you all remember our nulls have to be equal. So if we were trying to do this hypothesis test, this is the only way we could set it up, right? The null always has to be equal to. So if we're trying to prove it's more than a number, we have to assume it's equal to that until we can prove otherwise. Then if you reject it, so if you reject this hypothesis, so you reject this, then what you're saying is what? There is evidence mu is greater than 120. Right? So you're rejecting the null hypothesis is that it is 120 in favor of the alternative. So there is evidence that mu is greater than 120. So which one of those matches what I just said? That would actually be A. Yeah. Yeah, I feel like there's a word. Seems like there should be a sentence there at the beginning of that. All right, let's move on. All right. All right. So the Business College Computing Center, they want to determine the proportion of business students who have PCs at home. If the proportion exceeds 25%, they're going to scale back on a proposed enlargement. So they're saying, hey, if everybody's got computers anyways, we don't need to be spending a bunch of money on tons of computers. So suppose they take 200 business students and they find that 65 have PCs at home. So find a rejection region for this test if you were going to use alpha equals 0.01. So what is the hypothesis test that they're proposing right here? So is this a test about a proportion or a mean, by the way? This is a test about a proportion, that's correct, because we're talking percentages. Your null hypothesis is always equal to. So what is the null hypothesis here, and what is their alternative? They want to see if the proportion does what? Exceeds 25%?
Greater than 25%.
And would that have to be the null or alternative?
That would be the alternative.
Has to be, because the null has to be equal to. So they're thinking they might be able to show p greater than 0.25. Until then, they should just assume maybe it's equal to the threshold. Maybe we can show it surpasses that. And they want to do this at the what level?
0.01.
Mm-hmm. All right. So if you're doing the critical value approach, it's a greater than alternative. Where do you want to pile up all that alpha level? Up at the top. So we're going to put that whole 1% up here. And we're going to go find z sub 0.01. And you can we actually found this already back in another problem. But we go to our table. So if 1% is above, what percent's below? 99 below. So we're really looking for like the 99th percentile on our z table. So go to your z table. Where does it happen? I'm thinking about 2.33. 2.3, yeah, 0, 1, 2, 3. There it is. 2.33. All right. So then your rejection region is where? Above or below? Above. So this is our rejection region. So then our decision is going to be we're going to reject whenever our z value gets bigger than 2.33. Right? So anytime our z, so when we go calculate our test statistic and we calculate our z value, if it exceeds 2.33, we'll reject. So that looks like it matches up with option A. Okay? I just spilled coffee all over myself. Go me. All right. What else? 17? We'll do 17 actually because I had an online student who wanted to see that one. So this is the same. This is actually a similar problem, but they kind of changed the numbers on you a little bit. So it says, suppose the computing center, they want to determine the proportion of business students who have them. In other words, they're not coming up with some number in mind to begin with. But if the proportion differs from 30%, they're going to modify the way they were planning. So they're planning their facilities assuming 30% of people have computers at home. So what is the actual test they're performing here? What is our null and what is our alternative? Null is always equal, alternative could be something else. So the null is like they're assuming 30%. They're interested to see if what though? Yeah, this is going to be a not equal to alternative. So a two-tailed test. Yeah. Mm-hmm. All right. So it's a two-tailed test. Suppose a hypothesis test is conducted and the test statistic is 2.5. All right. So then find the p-value. So the way we conduct a two-tailed test, remember, in a two-tailed test, the rejection region is on both sides, right? So you have to half your alpha level to go on either side. But if you're going to do a p-value approach, what you have to do is, they said the test statistic was what? 2.5. 2.5. So if it was a one-sided test, the p-value would just be this probability up here. But in a two-tailed test, we actually have to double our p-value for a two-tailed test. So we need to go to the z-table. So if you go to the z-table and look up 2.5 or negative 2.5, say, I'll look up the negative one. Negative 2.50, it has 0.0062 below it. 0.0062. So that means there's 0.0062 down here and 0.0062 up here. And we combine the two tails. So together that would be 0.0124. And I think that would be your p-value. Yeah.
What about the, so the 2.5 you want to look on the t-table or the t-table positive?
If you look it up positive, it's going to give you the complement probability.
Oh.
Because if you look it up on, if you look up 2.50 on this side, it gives you 0.9938, but that's a complement. So you have to do 1 minus, and you'd also get 0.0062. But the nice thing about the symmetry of the z distribution is we don't have to do that. As long as we know the upper tail, we know that the lower tail, we know that the upper tail has to be the same. All right. So that's the answer. So that's just the trick. If you're doing a two-sided test, now we could have just done a confidence interval. I showed you guys that yesterday for the test. But if you want a p-value, you have to double it.
Can you go back to the diagram for a second?
Yeah. And but that's only in a two-tailed test. All right, that's still a pretty low p-value, right? Looks like probably the truth is not 30%. All right. All right. So these last three are not multiple choice. I might give you a couple hypothesis tests that aren't. So let's see. So an airline claims that their no-show rate for passengers is less than 5%. And so they did a sample. So at the 1% alpha level, can you actually test? We want to test that actual claim. Okay. So the null hypothesis and the alternative, the null always has to be equal to. So what's kind of the claim here? Or what are we trying to show or prove? So we're trying to show it's less than 5%. So less than 5% has to be what, our null or our alternative? Yeah, so the null hypothesis can never be less than. Yeah, so, or greater than, yeah. So then that means our null hypothesis would have to be 5%. So we'll assume it is 5%, and maybe we can show it's less than that. All right? We want to do this at the alpha, what was it, 0.01 level? Yeah, 0.01 level. Okay. And what's our p hat for this sample? 19 over 420, which comes out to be what?
0.04524.
0.45-ish. So it is a little lower. Does that decimal terminate or not? Or does it just keep going?
It terminates.
Yeah. What is it?
0.045238095.
Oh, wow. Okay, never mind. That's longer than I'll go 0.452, 0.0452. So there's just a little under 5%, but that could just be random chance, right? Maybe we just happen to sample a lot of on-time passengers, or a lot of passengers just showed up. So we want to test, and there's two ways to do it. We can do it with a critical value approach. So if we wanted to do the critical value approach, we could go get a cutoff, right? So our alpha level is 1%, and it's a one-sided test. So 1%, we just need to go get that negative z sub 0.01. And I think that's going to be a negative 2.33 if you look it up in your table. That would get you your cutoff. And once we have our cutoff and our rejection region, we're going to take all this information and calculate our z-score. So our z-score is always what? P hat minus the claim over the square root of the claim times 1 minus the claim over the sample size. So that's going to be 0.0452 minus 0.05 on top. Downstairs, square root of 0.05. 1 minus that would be 0.95. All over n was 420 people. So what do you get as your z statistic there?
Negative 0.45.
0.45? Yeah. So negative 0.45 is right here. Right? Is that in our rejection region? Mm-mm. So it's not in our rejection region, so what should we do?
Fail to reject.
Yeah, we'll fail to reject. So fail to reject H naught. So what are we actually saying? Are we saying that their rates look like is there evidence that they really are below 5% or not?
There's not enough.
That's right, yeah. So from there you would say there's not enough evidence to show that their rates are actually less than 5%. You know, this sample happened to be slightly below 5%, but as far as we can tell, that could just be due to random chance. Okay? So there's not enough evidence to suggest they're less than 5. Okay, any questions on that one?
So there wasn't enough evidence.
Right, so not enough evidence to suggest the truth is less than 5%. So I'll actually write that. Whoa. Not enough evidence. Their percent of no-show is less than 5%.
I have a question.
Okay.
So when you find the cutoff at 0.01, do you look outside or inside?
That's a percentile, so you're looking inside. See, so that 1% is a probability or a percent below. It's a percentile, so you're looking for 1% inside the table.
Okay.
And you're trying to map it back out to a z-score.
Okay.
Yeah. All right. Okay. Another one? Yes? Sure. A recent study claimed that 15% of junior high students are overweight. In a sample of 160 students, 18 were found to be overweight. At alpha equals 0.05 level, test the claim. So with no other information, what type of alternative should we assume here?
That it's not equal to.
Yeah, so with no other information given in the problem, we should just assume a not equal to alternative. Okay? So the claim is 15%, is that what it said? We're thinking maybe the truth is something other than 15%. Now, this is a two-tailed test, right? But yesterday I showed you can actually perform two-tailed tests using what? A confidence interval, and in my opinion, it's way easier to do it that way. So what we could do is, what's the alpha level here? 0.05. So our alpha level is 0.05, so we could actually just do a 95% confidence interval to do this test. Remember, it only works for a two-tailed alternative. But if you have a two-tailed alternative, you can do a confidence interval.
How do you answer 2 tails?
A two-tailed is when you have a not equal to alternative. Yeah. That means you don't have a premonition up front. It could be less, it could be more, we don't know. Okay. So what I'm going to do is I'm just going to calculate a 99 or 95% confidence interval based on my sample proportion. So by the way, what was our sample proportion? 18 out of 160, which comes out to be what? 0.1125? 1125, right? So then our confidence interval will go 0.1125 plus or minus. What's the z multiplier for a 95% confidence interval?
2.5.
That would be 99.
1.645.
That would be 90. How about 1.96?
What was it again?
Oh yeah, 1.6.
1.96.
Yeah. Yeah, 1.96.
Wait, no one.
Yeah. We're doing a 95% confidence interval, right? So the multiplier for 95% confidence is 1.96. And so that's 0.1125. 1 minus that would be something like 0.8875, I think. All over, our sample size was 160? Yeah. Okay. What do you come up with that margin of error if you try that out? 0.1125, 0.8875, divide by 160, take the square root of that, multiply that by 1.96. I get 0.0490 basically, 0.049. Anybody else able to get that? 0.049. Okay. So then we would subtract it and add it. So if you take 11.25 and you subtract 40, what is that? 0.063 something? 5. And then add it up, and what do you get? 1, 2? No, 1, 6? 1615? Okay. So the way you use the confidence interval then is we got our confidence interval, and so we say, is the claim contained inside that interval? So does this interval cover 15%? It does, right? So notice that 0.15 is in this interval. Okay. And so that basically tells us that 15% seems reasonable. Seems like it could be the truth. So we should not reject that claim. So since 15% is in the interval, we're essentially going to accept the null hypothesis, but we don't ever actually say accept. So then our decision here should be fail to reject the null hypothesis. Okay.
I like the other way better.
What's that?
I like the other way better.
What, a critical value? Yeah. And you can do it. You could do it as a critical value. You would just have to, so your alpha level is 0.05, right? So since it's a two-tailed test, we'd have to split that in half, right? Which would give us cutoffs of 1.96 on top and bottom. Yeah. And then if you calculate your z value, it would be that would be, p hat minus the claim all over the square root of, over n, which was 160. Right? And you could get a z value.
I get a 1.33.
So a z value of about 1.33 or so. Yeah, and that's also, notice, not in the rejection region. So you would still come up with the decision of fail to reject. Yeah. So if you like the formulaic way and just say, you know what, I know how to do critical values, I'm going to do critical values, then just do critical values. It'll come up with the same answer. All right? Yeah. Either way works just fine.
Like not enough evidence.
Yeah, so then what is the actual conclusion here? It says, are we saying that it looks like that the overweight percentage is 15% or is not 15%?
It is not enough evidence.
Yeah, so we would say basically there's not enough evidence that P is different than 15%. So as far as we know, it looks like it could very well be 15%. I don't know. As far as we know, seems reasonable. 19? 19. Okay. Anybody want to stick around for 20?
Yes.
20 is actually not too hard because they kind of give us all the information we need to make a decision. So increasing numbers of businesses are offering childcare. One union claims that more than 85% of firms still don't do it. So they sampled manufacturing firms and asked if they offer childcare benefits. And they said, this is the p-value they reported. So what is the hypothesis test they're doing? What are they thinking they could show versus what do we need to assume the null is? Yeah, because their claim is that it's more than 85, right? So what happens is they do the test and they get a p-value of 0.1074. Is that right? But they're going to they decided to test it at an alpha level of 10%.
It's 1070 for the p-value.
1070. Okay. All right. Then what should be your decision? Is our p-value bigger than our alpha level or smaller? Which one's bigger? Yeah, so you notice our p-value actually exceeds our alpha level a little bit. So if our p-value exceeds our alpha level, then should we fail to reject or to reject?
Do not reject.
Yeah, don't. Remember, we only reject for low values of low p-values, right? So if your p-value is high, then you don't reject. So the p-value is bigger than our alpha level, so we should fail to reject. And so what would we say here? So fail to reject is when we say there's not enough.
Evidence is destroyed.
Yeah, so there's not enough evidence to suggest, that the proportion is over 85%. Not enough evidence. So as far as we can tell, it looks like the truth could be around 85%. I don't know. We don't know. We just don't have enough evidence to say that it's more than 85%. All right. Hey, we did.